Welcome to part 2 of the video podcast series that addresses combustion analysis. In part 1, we dealt specifically with compounds that contain only carbon and hydrogen. In part 2, we're going to add elements to carbon and hydrogen. So, hence the subtitle, Compounds Containing Elements Along with Carbon and Hydrogen. If you haven't watched part 1, please do so, or this one probably won't make a lot of sense to you. Welcome. The principles and basic steps of how to solve combustion stoichiometry problems or combustion analysis stoichiometry problems are found in part 1. If you haven't watched part 1, please go back and do so. Take notes on that, because for part 2, we're making the assumption that you already know the basic steps and understand them, and we're going to go right into sample problem solving. So our first problem, we're going to deal with a substance called quinone, which is an organic compound that contains only carbon, hydrogen, and oxygen. Combustion of 0.105 grams of quinone yields 0.257 grams of carbon dioxide and 0.0350 grams of H2O. If its molecular weight is approximately 108 grams per mole, we want to determine its empirical formula and its molecular formula. Now, a great way to approach this would be to pause the podcast now and work through this problem as much as you can. Solve everything that you can, meaning right off the bat you should be able to get to the mass of carbon and hydrogen quite easily. The mass of oxygen will be found by subtracting the masses of carbon and hydrogen from the total mass of the compound that you combusted, and see how far you can get with this in terms of determining the empirical molecular formulas. Resume the podcast and we'll see how you did. Welcome back. Let's see how you did so far. To find our grams of carbon, we took the mass of carbon dioxide, 0.257 grams, multiplied it times the mass ratio of 12 grams of carbon for every 44 grams of carbon dioxide, and we've got 0.0701 grams of carbon. For our grams of hydrogen, we took 0.0350 grams of water times the mass ratio of 2 grams of hydrogen for every 18 grams of water, and we got 0.00389 grams of hydrogen. We found the masses of the carbon and hydrogen in a traditional way. We have to find the mass of oxygen a little differently, because when we combust a compound in excess oxygen, the oxides that are formed, water and carbon dioxide, are going to contain not only oxygen from the compound itself, but oxygen from what was added for the combustion process. So in order to find the oxygen, we have to subtract the sum of the masses of carbon and hydrogen from the mass of the original compound to find the mass of oxygen. So the mass of our original compound was 0.105 grams, and we're going to subtract from that the sum of 0.0701 grams of carbon plus 0.00389 grams of hydrogen. When we do that, we get 0.105 grams minus 0.0740 grams, and we're left with 0.0310 grams of oxygen. Now that we have the grams of carbon, hydrogen, and oxygen, we can convert them to moles. And so our grams of carbon, 0.0701 grams of carbon times the conversion factor or equality 1 mole of carbon over 12 grams of carbon gives us 0.00584 moles of carbon. Our 0.00389 grams of hydrogen times 1 mole of hydrogen over 1 gram of hydrogen gives us 0.00389 moles of hydrogen. And finally, for our oxygen, 0.0310 grams of oxygen times 1 mole of oxygen over the molar mass of 16 grams of oxygen gives us 0.00194 moles of oxygen. Now that we have the number of moles of each, we can find the mole ratio by dividing all the mole quantities by the smallest. The smallest quantity is the 0.00194 moles of oxygen. So for carbon, we take 0.00584 moles divided by 0.00194 moles, and we get 3 moles of carbon. For hydrogen, we get 0.00389 moles of hydrogen divided by 0.00194 moles, which gives us 2 moles of hydrogen. And for oxygen, it's very nice here. We take 0.00194 moles divided by 0.00194 moles. So we get 1 mole of oxygen. So the mole ratio is 3 moles of carbon for every 2 moles of hydrogen for every 1 mole of oxygen. And now we can write the empirical formula C3H2O. Now that we have the empirical formula, we can find the empirical formula mass, and then we're going to divide the molar mass by the empirical formula mass so that we can determine the molecular formula. The empirical formula is C3H2O, so its mass would be 3 times the 12 grams of carbon, 2 times the 1 gram of hydrogen, plus 16 grams of oxygen. So we get 54 grams per mole for our empirical formula mass. Our molar mass is 108 grams per mole, so we divide that by our empirical formula mass of 54 grams per mole, and we get a lovely mass ratio of 2. Once we've found the ratio of our molar mass to our empirical formula mass, we can multiply that ratio by the subscripts in the empirical formula to determine the molecular formula. So our empirical formula is C3H2O. We multiply each of those subscripts by 2, and we get, for our molecular formula, C6H4O2. How'd you do? Well, we're ready for a more complex problem. Let's look at this one. Combustion analysis of an unknown compound containing only carbon, hydrogen, and nitrogen. 12.923 grams of carbon dioxide and 6.608 grams of water were measured. Treatment of the nitrogen with hydrogen gas resulted in 2.501 grams of ammonia, which is NH3. What is the compound's empirical formula? We're going to use the mass ratios to find the grams of carbon, hydrogen, and nitrogen. Our grams of carbon, simply 12.293 grams of carbon dioxide times the mass ratio of 12 grams of carbon for every 44 grams of carbon dioxide gives us 3.3526 grams of carbon. For our grams of hydrogen, it was 6.608 grams of water times the mass ratio of 2 grams of hydrogen for every 18 grams of water, which gives us 0.7342 grams of hydrogen. Now, we haven't used the mass ratio of nitrogen in ammonia in a problem yet, but it's very straightforward. We have 2.501 grams of ammonia, NH3. We multiply that times the equality of there are 14 grams of nitrogen in every 17 grams of ammonia. When we do that, that ratio of 14 over 17 times the 2.501 grams of ammonia gives us 2.060 grams of nitrogen. Now that we have the grams of carbon, hydrogen, and nitrogen, we can convert each of those to moles. So our 3.3526 grams of carbon times 1 mole of carbon over 12 grams of carbon gives us 0.27938 moles of carbon. 0.7342 grams of hydrogen times 1 mole of hydrogen over 1 gram of hydrogen is equal to 0.7342 moles of hydrogen. And finally, our 2.060 grams of nitrogen times 1 mole of nitrogen over 14 grams of nitrogen gives us 0.147 moles of nitrogen. We're ready to move on to our mole ratio, and then we'll have the empirical formula. Let's go ahead and find the mole ratio of each by dividing all the mole quantities by the smallest. The smallest in this case is the 0.147 moles of nitrogen. So for carbon, we take our 0.27938 moles and divide it by 0.147 moles, and we get 2 moles of carbon. Now when you do this in your calculator, you're going to get 1.9, and you just have to round that to the nearest whole number. There's some numbers you won't round up or down. You'll use the multiply to a whole function that we use for empirical formulas, but this is close enough to 2 to go ahead and round it. For our hydrogen, our 0.7342 moles divided by 0.147 moles gives us 5 moles of hydrogen. And for nitrogen, of course, the 0.147 divided by 0.147 gives us 1 mole of nitrogen. So our mole ratio is 2 moles of carbon for every 5 moles of hydrogen for every 1 mole of nitrogen. So we get an empirical formula of C2H7N. N. Now, this second sample problem that we did shows that when you have elements other than carbon, hydrogen, and oxygen, you often have to find the amount of the other element, in this case nitrogen, through a different experimental process. And in what this particular process was, they took the nitrogen and reacted it with hydrogen gas to form ammonia. So you just had to have a second process in order to determine that, and you'll see that done several different ways as you confront these type of problems. Hope you did well with that. There will be a third part to the combustion analysis problem sets or video podcast sets that will deal with a little bit more complex problems than these. So stay tuned and engage those when you're ready. Well, we're at the end of part 2 of the video podcast series having to do with combustion analysis. I want to leave you with a quote from Mark Twain. "Against the assault of laughter, nothing can stand. May you laugh much in this life." I wish you well.